Thank you, everyone, for inviting me to speak to you tonight. I'm going to try to tell you about what's going on in our search for other habitable worlds similar to Earth. And so you might wonder, why is part due in the title? Well, there's one main reason. It's not just Charlie Sheen, but it's also that I gave a talk with this title almost 2 decades ago, back in 2006, a neighborhood lecture series at our campus in Northwest Washington, D.C., where I summarized what happened in the first 10 years since the discovery of the first exoplanet around a sun-like star in 1995. We made a lot of progress by then, but we've had another almost 20 years of progress since then. And so what I want to do is start off tonight by telling you what we knew as of 2006, then moving on to what we know as of 2025 and what we expect to learn in the next couple decades. So to start off with, why is it so hard to take a picture of a nearby Earth-like planet? The problem is that you're next to something very bright. This shows you the light emitted by a reflected Earth at optical wavelengths in this region here, which is about 10 to the 10th times fainter, or 10 billion times fainter than the star that's right next to. So at optical wavelengths, the Earth is basically as bright as a 30th magnitude star, which is pretty hard to observe. It actually could be done by the Hubble Space Telescope. The number of faint galaxies in the Hubble deep fields, the extremely deep fields that are 30th magnitude objects. So it could be done by a telescope by Hubble, relatively modest 2.4 meter diameter telescope. The problem is that you're right next to something which is 10 billion times brighter, and that's what kills you. It's the contrast between the two. So we've known for some time that it was not going to be easy to just take pictures of Earth directly. Though you notice, though, if we went out to mid-infrared wavelengths, say 10, 20 microns, because of the thermal emission from the planets, Earth and Jupiter, the gap in contrast you need to overtake is only about a factor of 1,000,000. And the problem is that you only gain that by going to a 10 times longer wavelength, and that means in order to resolve something, you've got to have a 10 times larger telescope. So we're already talking about big telescopes, and so it's not exactly easy to just simply go to mid-infrared wavelengths and solve the problem that way. So because of that, the fact that direct detection, we knew for some time, was going to be a challenging way of detecting planets, most of the work that's been done so far is through indirect detection. And this goes back to the basic old trope we're told in elementary school about all the planets revolve around the sun. Well, it's not quite true. The sun also revolves around the center of mass of the system. And that's the key thing is, in the case of our solar system, Jupiter is 1,000 times less massive than the sun. That means that the sun orbits around a center of mass, which is 1 solar radii away from the sun. So if you could see the sun from a nearby star and watch Jupiter revolve around the center of mass every 12 years, and the sun revolve around that same center of mass, it would go around basically wobble back and forth over a distance equal to its diameter every 12 years. And that's a pretty small angle to measure. It's not trivial. It's about, for a Jupiter mass object at a typical stellar distance of 10 parsecs, or 33 light years or so, that would be an angular displacement of about 1 milliarc second. And that's just to give you a feeling for it. That's basically the size of a dime as seen at 1,000 miles. So it's a pretty tiny angle, but astronomers have been trying to measure that and to do even better than that, in fact, because we hope to eventually be able to perhaps measure the wobble due to Earth-like planets, and that's about 1,500 times smaller. So that would be a microarc second wobble on the sky, which is, you can imagine, over 1,000 times harder to measure. So this is the basic idea: is you start off by see if you can measure a wobble of the star on the sky. And the first way that's what's applied is the old-fashioned way of astrometry, where you actually literally measure the position of the star on the sky. And the key object from that search is Barnard's star. Barnard's star was discovered in 1919 by Edward Emerson Barnard, who was an amateur who became a professional astronomer. He liked to take pictures of comets and detect comets. In the process of trying to find more comets, he stumbled across Barnard's star, which turns out to be the closest star to the sun, other than the Alpha Centauri binary triple system with Proxen. And so a very close by star is exactly what you want, because the closer you are, the bigger the wobble is. If you're 10 times closer, you got 10 times bigger wobble to see on the sky. The other great thing about Barnard's star is that it's a very low mass, red dwarf star with a mass only about 1/7 the mass of the sun. And that means that compared to the sun, its wobble is 7 times larger, all of the things being the same. So this was a perfect sort of star to be trying to looking for a wobble indicative of having a Jupiter mass planet around it. So the key thing about the star is in 1937, Peter Van de Kamp became the director of the Sproul Observatory at Swarthmore College. And in 1938, he began a long-term program of studying Barnard's star every single year, every time he could get an image of it. And so he took data for 25 years and measured the plates, and had a whole series of undergraduates measure the plates for him and try to average out the observational bias in measuring plates. After 25 years of observations, he was finally ready to publish his detection of a Jupiter mass planet in orbit around Barnard's star. So shown here are the right ascension and declination. Basically 2 axes on the sky, showing you the data points, where the bigger the data point, the more you believe them, the smaller the data points, the less you believe them. You can see sort of, he's assuming he's got a full 24-year orbital period here. So these data points here are actually the same as these data points, assuming that it's repeating itself. And you see a nice wobble up and a wobble down, both RA and declination. And it's actually a wobble of about 10 milliarc seconds, which corresponded to actually a displacement of about 1 micron on the scale of the plates that he was using for this 24-inch Sproul refractor. So this was interpreted by Van de Kamp as evidence for a 1.6 Jupiter mass object in orbit around Barnard's star, out at a distance about 4.4 AU, so similar actually to Jupiter's distance. The only odd thing about it is it's a somewhat eccentric orbit. If it was a nice circular orbit, which Jupiter's orbit is pretty circular, it would be a pure sinusoid. This has a little bit of a shape to it. So this literally became the accepted version of a Jupiter mass planet around stars. People assume there should be some out there, and it entered into the textbooks. So everything was fine in 1963. We found the first extrasolar giant, or gas giant planet. And that unfortunately changed because around 1973, a colleague of mine, George Gatewood, and his thesis advisor, Heinrich Eichhorn, who's sort of the dean of precision astrometry, Eichhorn has suggested to George that why don't you take another look at Barnard's star and see if it's really there, that wobble that Peter Van de Kamp had seen. So Eichhorn tasked Gatewood was using a completely different set of material taken from a Van Vleck observatory telescope, and rather than have students take a look at the photographs and try to measure wobbles or displacements on the plates, they used at the time was a brand new plate measuring machine that the U.S. Naval Observatory in Washington, D.C. had just come up with. And with Eichhorn's connection, Gatewood was able to get the plates measured there. And after analyzing the plates, he again had another 24 odd years of data or so, and he plotted just sort of one coordinate axis of the wobble that was expected, and the dashed line is what Peter Van de Kamp's orbit would have suggested. And again, the larger the point is, the more you should believe it. And these points here are duplicated over here, assuming he's got a complete orbit. And so, these 4 points here and these couple points up here don't seem to fall on Van de Kamp's curve. These points look pretty good, but the big heavily weighted points don't. And this one here, you should just neglect altogether because that's actually a fleck of dust that came over when I used to give this talk with a 35 millimeter slide. And in translating from 35 millimeter slide to a PowerPoint, that fleck of dust stayed on that image. But I think Peter Van de Kamp would have used that as evidence for the planet, but clearly it's not very good evidence. So at this point, Gatewood and Eichhorn rather gentlemanly said that they saw no evidence for the planet around Barnard's star, and it began to disappear from the textbooks again. So the astrometry did not work out so terribly well. The very first one basically disappeared. But there's another way of looking for a wobble, which is in the radial velocity. Again, as the star and its planet wobble around the center of mass of the system, the light emitted by the star in either absorption or emission lines is redshifted periodically back and forth with the period of the orbit. And in the case of Jupiter going around our sun, it makes the spectral lines of the sun wobble by 13 meters per second every 12 years, which is about 30 miles per hour. So 30 miles per hour doesn't sound like very hard to measure. I mean, certainly if you have a speed camera around here that's going to get you if you're 30 miles per hour of the limit. But the problem is it's 30 miles per hour relative to the speed of light, which is about over 10 to the 7th times faster than that. So you're looking at a fraction of a shift in wavelength of more than a factor of 10 million. A pretty tiny shift to measure, but astronomers, being clever folks, have worked very hard to come up with spectrometers that could measure that sort of a small wavelength. I should point out here also that if you're trying to measure Earth's wobble, Earth's wobble is instead of being 13 meters per second, it's over 100 times smaller. It's about 9 centimeters per second, but over a 1-year period back and forth, which makes it pretty tough. But people are actually talking about doing that in the future. Okay, so here we have the idea of trying to find a planet by the radial velocity wobble, and a number of astronomers have been working on that for some time. It's not. It was actually more promising than astrometry, and the ones that hit pay dirt first were Michel Mayor and Didier Queloz. Using the 2.2 meter telescope at Habitable Observatory in southern France, they observed this solar twin, 51 Peg. It was one of 100 solar twins they'd been looking at. They had already done a survey of binary stars, and they found roughly 100 solar twins that didn't seem to be in binary. So they thought, well, maybe they've got something else orbiting around them. So they followed those 100 stars, and after a couple of years of observing, they found this one, which had a nice, clear, clean wobble. There's one data point here that doesn't quite fit. Not quite sure what happened that night, but the rest of the data points fit this line very nicely of a nice sinusoidal curve. It implies it is indeed a circular orbit, similar to that of Jupiter. The amplitude of the wobble here, about 55 meters per second, is what you would get for roughly a half Jupiter mass object. So that all sounds perfectly fine. The big surprise about this, though, was that the orbital period is not 12 years, it's 4.23 days. That is such a short orbital period that its orbit is 100 times closer to its star than Jupiter's is. It's out at a distance of 0.05 AU, 1/20th of the Earth-Sun distance, and it's actually out at about 10 solar radii for its star, 10 stellar radii, I should say. That means it's so close to its host star that it is a hot Jupiter. It's got a temperature, surface temperature in thousands of degrees, and that was a bit of a mystery, especially to someone like me. I was asked by Nature to be one of the reviewers on this paper, and I think 2 other astronomers were also reviewing it because we'd never seen anything quite like this. We were not expecting to find a gas giant down so close to a star with such a high temperature. We were still battling with Mayor and Queloz over the referee report when Michel Mayor spilled the beans at a conference in Florence, Italy, and said, he just couldn't keep the secret anymore. In spite of Nature embargo, he let out the news what he had seen, and so that meant a number of astronomers rushed to their telescopes to see if they can confirm it or not. And the 2 that won the prize for confirming it first were Jeff Marcy and Paul Butler, my colleague Paul Butler at Carnegie. This is a really crummy slide they sent me back from we were doing 35 millimeter slides. They didn't have much money to make good slides, but it shows that they took data over a 4-night observing run. There's only a 4.23 day period. So if you just hammer it all night long for 4 nights, you will either prove it or disprove it. And they said, yeah, it is there, it is real. So at that point, I think that nobody cared about our Nature referee report. Nature went ahead and published the paper because it was clear this is a real object with the 4.23 day period. So that was basically the beginning of the year. That is now just as of 30 years ago this summer. That will be when in 1995 that it was first detected by Mayor and Queloz and first published in Nature. So we're right on our 30th year anniversary. A number of celebrations being planned for that anniversary this summer. Okay, so what is another way of finding planets indirectly? A second way, besides astrometry and radial velocity, or I should say a third way, is a transit. If the star happens to have its planet's orbit aligned so that the planet passes right in front of the star and transits, or assuming if you had enough photometric precision, you could also see the planet pass behind the star and be eclipsed. But the idea is if you have a transiting planet, that might very well be enough to see a star dim. And of course, it's not easy to do that because you have to have the planet's orbit aligned correctly. Unless you're very close to the star, the orbits are not likely to be aligned. But if you have a hot Jupiter, there's a pretty good chance that it will be aligned. In fact, there are like, if you have 10 hot Jupiters, one of them should be aligned in order to produce a transit. And that's exactly what happened around the star called HD 209458b. A couple of astronomers detected the passage of Jupiter in front of its star. Now, just to show you how tough this is an image from one of your Northern Virginia astronomers, Bob Traub, who gave it to me a while back. This shows not a Jupiter in front of the sun, but this is actually Venus transiting the sun, which makes for a gorgeous image. The problem is that with a Jupiter passing in front of its star, Jupiter is only about 10 times smaller in radius, and so it blocks 1% of the starlight. So you would see a star suddenly dim by 1% and then brighten up again once the transit ended. And that could actually be done. 1% photometry can be done from the ground with a good system. In fact, that planet I told you about with the HD 209458 was actually detected with a 10-inch telescope in the parking lot in Boulder, Colorado by Tim Brown and David Charbonneau. But if you're going to try to find an Earth-sized planet, and Venus is pretty much the same size as Earth, you're 10 times smaller yet. So that means that you are only dimming 1 part in 10,000 of the light. So you've got to do 100 times better, and there's just no way you can do that from the ground underneath our atmosphere bubbling and boiling all night long. So that means if you really want to do that sort of thing, you need to think about doing it in space. And so back in 2006, we were anticipating the launch of the Kepler mission. It was only about a year or so off at that time. The idea was to fly the special built telescope, which has a 95 centimeter Schmidt collimating lens on the front and a 1.4 meter primary in the back, and at the time the largest camera that ever been launched in space, and have it just stare at one area near the Milky Way for about 4 years and look around solar type stars and want to see if there are dimmings due to Earth-sized planets on Earth-like orbits. So you'd want to wait and see a planet dim by a part in 10 to the 4, wait roughly 1 year later if it's out of the habitable zone like the Earth is, and see a second dimming, and then just to confirm it, you want to wait another year later and see a third dimming. So if you see 3 dimmings at the same period, you're reasonably sure you may have something there. Of course, it could still be a background eclipsing binary fooling you, but at least you have a really good candidate. And so the idea was to launch this mission and look at this, stare at the same area of the sky for 4, 5, 6 years and see how many Earths they could find. So that was pretty exciting. Where we were in 2006, this is just 1 year away. There also were plans at the time to do a space-based astrometry mission to actually look to the Van de Kamp technique to look for the wobble. Remember I told you for Earth, the wobble is about a little bit less than a microsecond, about 2/3 of a microarc second. And the Space Interferometry mission was designed to measure wobbles to a precision of 1 microarc second. It was to do this with it's a 10-meter long optical telescope with the 2 siderostats, which is flat optical flats on either side, and a beam combining a very complicated interferometer sitting in the middle, which would look for nulls as a planet wobbled back and forth, and it could measure the distance of the star with the presumed planet with other reference stars to see if it actually was wobbling at the level of 1 microarc second. The plan was to be able to fly the spacecraft and maybe return to the same system 100 times or so, and then use root n statistics to knock down the noise by a factor of 10, and so get down to a level where you could actually detect a wobble of 2/3 of a microarc second. At that time, we were pretty optimistic. It was going to launch in about 2010. So we're just a few years off. A lot of technology had gone into developing the spacecraft concept. I spent many trips to Los Angeles going to Jet Propulsion Laboratory overseeing the plans for developing the technology for this mission. We were even more ambitious at that time, which was, let's see what we can do about direct detection. And for that, you need a coronagraph. And here's about the most perfect coronagraph you can ever conceive, which is the moon passing in front of the sun during a solar eclipse. You can see the moon does a great job of blocking out the sun's light and revealing the sun's corona, which is why it's called a coronagraph. It's a natural chronograph, but what you need to do is develop a much better chronograph, which astronomers who like to study the sun build their own chronographs and mount them on telescopes. But even still, we really want to block out all this other light that's coming around the edge, because this is still a killer. All this other light diffracted around the edge and emitted by the sun's corona would block out any planet having to be orbiting around the sun. So And because of that, again, JPL technicians had worked for years developing very advanced coronagraph concepts. In particular, the hybrid LEO coronagraph was developed to be flying on something called the Terrestrial Planet Finder Coronagraph, which at the time we thought might launch in another 10 years or so, 2016. So here is a sunshade to block other starlight, and here would be a primary mirror. It would be about 4 meters by 8 meters, elliptical shape. You really wanted the 8 meters to give you the resolution you need to pick out the planet light from the sun's light after you block the sun's light with your internal coronagraph. And that odd shape of being elliptical was because at that time, the largest launch vehicles we had available to us was the Atlas V, which had a 4.2 meter fairing. So you could not launch anything wider than 4 meters, say, in order to give you a little bit of room. So it's a 4 by 8 meter. That's fine. You just put that 4 by 8 meter up there and rotate it a little bit and let that 8 meter aperture help you detect the planet. I should point out, by the way, that in the future, Starship, SpaceX has a Starship which has a 9 meter fairing. So we could launch something really big in the future if we wanted to. Okay, so that's where we were in 2016. And we were even talking about going to mid-infrared wavelengths and launching a mid-infrared interferometer. This would have to be 100 meters in size. No way to build a single telescope that size. So instead, the idea was to have 4 auxiliary telescopes, each about 1.5 meters in size, and let them combine their beams with each other and with a processing nulling test bed. And again, look for wobbles, and even moving these, changing the spacings of these 4 unit telescopes, you can actually create a picture, so-called painting the UV plane. And you can actually image at mid-infrared wavelengths and take a picture of the planet and learn something not only about its existence, but also about its atmosphere. And at this point, even the Europeans were pretty excited about it. They had their own concept for this. And back then, NASA and European scientists were working together, and they'd come up with a concept that they called the Emma Darwin interferometer, sort of a play on Charles Darwin, who's important for theories of evolution. But they decided, let's just not name it after guys all the time. Let's call it the Emma Darwin, named after his wife. So Emma Darwin was the concept that was jointly proposed by NASA and ESA. And this has actually been sort of approved by President George W. Bush. In 2004, he had given a talk where he said, we really need to look for planets around other stars and find other habitable worlds. And so those of us who were involved in these efforts thought, oh my God, this is really great. We've got support from the administration. The problem was it was an unfunded mandate. Bush called for it to be done, but no one gave us any extra money. So it makes it kind of tough to build something as ambitious as this without having a real support from Congress as well as the administration. So here's where we were in terms of discovery space after 2006, showing you the masses of objects, the units of the Earth masses on the vertical axis, and how far they are from their sun. So here at Earth and Venus, we're trying to hope to find objects here in this blue box, which is sort of the habitable zone for solar type stars. And what we found was a lot of hot Jupiters like HT 209458b and 51 Pei, a fair number of colder Jupiters and warmer Jupiters. A few things have been actually imaged by very distant, very bright objects, could be seen with existing telescopes. And there are a fair number of things down in this area here, which were sort of unexpected. They're sort of super Earths or sub-Neptunes right now. Many of these many more would be found by transits once Kepler would fly. But at this point, these have all been found by ground-based radial velocity surveys. And given that as you go farther in this direction to the lower right of this plot, things get harder and harder to find, whereas up here, things are easier and easier to find. The fact that you're seeing anything at all down here implied that if you could sort of drop the veil obscuring what's down here, we're going to find a lot of planets in this area here. That was the hope. Okay, so that was here's the conclusion slide from that 2006 talk. We already have evidence of many of the same things we're looking for in our solar system: gas giants, ice giants, and terrestrial planets. Although we don't, some of them might be more like water worlds rather than rocks like Earth. And there were even estimates published based on the radial velocity searches that the frequency of habitable planets, that is those orbiting at a distance where water could be liquid at the planet's surface, might be of order of a tenth. which is remarkably high when you think of all the billions of stars visible at night. If 1/10 of them have Earth-like planets, that is astounding. So at that point, we were pretty happy about what's going to happen. Oh boy, Kepler's about to launch. We'll probably have SIM a little bit later, and the terrestrial planet finders. I thought, wow, this is going to be wonderful. Okay, so, well, what actually happened? Well, the Kepler mission got delayed by a couple of years, but it did launch in 2009. Had some cost overruns, ran up to about $240 million as the total cost. And at one point, it was faced with a cancellation review, which is the worst thing a mission can face, because you could actually just be stopped completely, but it survived the cancellation review. It did fly for 4 years, and it was intended to discover roughly 50 Earth-like planets. That's what it was told to do. That's your measure of success, is find 50 Earth-like planets, and we will declare you to be a great success. So it did fly, and one of the first objects it looked at was a known hot Jupiter called HAT-P. The HAT stands for Hungarian Automated Telescope, which is down on at Las Campanas in Chile, Carnegie's Observatory. So it was a known hot Jupiter. You can tell it's a hot Jupiter because you see the transit depth here is about 1% or so, which means it's got to be something like a Jupiter size or Jupiter mass. And so the Kepler could measure that depth really well. It could also measure the eclipse on the back when the planet passes behind the star and its reflected light is being blocked by the star itself. And so this is able to measure on this blown up scale here. You can see quite clearly not only the transit, of course, but this 1 part in 10,000 eclipse, which is just sort of the level we're looking for. But you also can see, though, if you subtract out the transit and the eclipse, that there's still a lot of noise back here. That turned out to be one of the problems with the Kepler assumption. Was we assumed that if the stars themselves are their photometry, their brightness is changing in an irregular fashion, then that's going to make it hard. I mean, that's what we're seeing here, is this bubbling up and down, is the star itself churning through its convective outer layers. And we were using the sun as a model. The sun turned out to be a very quiet star. It turns out a lot of stars are a lot more vigorously convecting and changing in their intrinsic brightness than the sun is. And so that made Kepler's mission a lot harder than we thought it would be when we were planning it. So here's actually what came out as of 2017. So the mission ended in 2013. It ended sort of prematurely because it had 4 reaction wheels, which are like gyroscopes to help steady the pointing of the spacecraft. And first one failed, and then another failed. And at that point, you only had 2 gyroscopes left to steady the spacecraft. They could no longer do the sorts of precision photometry that it was intended to do. They still ended up doing the Kepler K2 mission, and did what they could with 2 and then 1 gyroscope, but they could not achieve the precision that the original Kepler mission could do. So here's what the big payoff is for the $640 million. They basically found under here, here's what we're looking for is, it's a function of how bright the star is. So it's basically stellar type with G dwarfs up here and M dwarfs or red dwarfs down here at the bottom. So we're looking for things here like Venus size and Earth size. There's really only 1 blue dot here confirmed. There are a couple of candidates, some new candidates, some older candidates. Fair number of interesting looking planets around M dwarfs. They're easy to see because their habitable zone is in closer to their star, and so you have many, many transits to be sure that you really are seeing a transiting planet. But they also didn't really come up with even 1 definite Earth-like planet. But even still, if you sort of do and there's still arguments going on about exactly what so-called ADAS of Earth is, the fraction of Earth-like planets. But the most recent predictions by those on the Kepler team, they say they think ADAS of Earth, based on sort of extrapolating into the unknown, based on the places where they could see them and how many planets were found there. They think ADAS of Earth might be as high as 0.6 or 0.8, which is again still amazing. You know, suppose over half the stars in the sky have an Earth-like planet. That should give you something new to think about next time you walk out and look at the dark sky and wonder about what might be looking back at you. All right, so that was all in all reasonably successful. Did not get the 50 Earths that were promised, but we got a pretty good estimate of ADAS of Earth. So another thing that comes along every 10 years in astronomy is decadal surveys. The National Academy of Sciences sponsors these, where they get number of distinguished astronomers together. They sit down and for a year or so and debate in closed session what the field should be doing for the next 10 years. And the Astro 2010 decadal survey came along. I was proud to be a part of it. Although I should say that the group I was involved in did not particularly care for exoplanets, which you can see from the top line. The electromagnetic observations from space group that I was on killed the SIM mission. $600 million been spent on it, and forgot about both TPFs. That was basically the end of what we thought was the most exciting exoplanet science at the time. And it's one of these things where you choose the committee, you choose your decision. I think we had something like 16 people on the committee, and 4 of us were interested in exoplanets. Guess what? We got outvoted. Okay, the one sop that they threw to us was microlensing, which I'll explain to you in more detail in a moment. But really, the one that, given how expensive these missions are, we really knew that basically whatever our top ranked mission was, we'd be lucky if even that flew, much less second or third ranked mission. So I think SIM came in basically second or third rank, but we knew there's no way that was going to fly. So instead, they created the W first mission, which is basically driven by the folks, the majority of the committee, which were extragalactic astronomers who wanted to study dark energy. But they did throw, it turns out the W first mission would also support a microlensing survey quite nicely. So they made it a combined mission to do both fields. Just a couple of years later, after it was decided to NASA would do this, it was renamed the Roman Space Telescope, and was given a little bit of a boost because it turns out the National Reconnaissance Office had some optics that had been developed that were Hubble class, built by the same laboratory that built Hubble. They were planning on flying a couple of similar 2.4 meter optics systems to look at the Earth. And we had a bit of a battle with the National Reconnaissance Office. I was actually part of a meeting at Princeton trying to decide what we could do with these optics. And the National Reconnaissance Office says, well, NASA can have it if you want, but you cannot look at Earth. And so even within NASA, there were some folks who wanted to use these optics to study Earth's aurora, which would have made a great way for characterizing the Earth's aurora. But NRO said, nope, that's looking at the Earth. You cannot do that. But looking out at the universe, that was perfectly fine with NRO. So we got approval to use those optics, which we thought would help lower the cost of the mission. That's what it looks like now. It looks very much like a Hubble, sort of stripped down. It was renamed the Roman Space Telescope, named after Nancy Grace Roman, who was the chief astronomer of NASA for many years. She's the lady who basically got the Hubble Space Telescope to fly. And the fun thing is that she's also was a good friend of Vera Rubin, who's an astronomer, my office mate for many years at Carnegie. So there's this Roman Space Telescope which will fly just a little over 2 years from now, perhaps. And I was at a conference at Caltech last summer where they talked about what the Roman Space Telescope will do in concert with the Rubin Observatory. Rubin Observatory is the LSST, large-scale synoptic telescope in Chile. It's an 8-meter class telescope down by the U.S. Observatory in Chile, and it will basically take a snapshot of the sky every night or two. And these young kids at this Caltech meeting were talking about Roman's going to be working with Rubin, and they had no idea that Nancy Grace Roman and Vera Cooper Rubin were actually good friends of each other. And Vera would often have Nancy come to our seminars at Carnegie, and the two of them would sit and ask really pungent questions of young astronomers who had no idea what these very sharp older ladies in the back of the room, that they knew much more about astronomy than they did. So it was often a big comeuppance from them. So it's a wonderful thing to hear that Roman will be working with Rubin, because I know both of these ladies quite well. So this is going to be flying in 2027, not too far off. It will be doing dark energy, but it will also be doing microlensing. So what is microlensing? This was something that Albert Einstein proposed back in 1936 or so. He never thought it would be practical to occur, but someone egged him into writing a paper about it. So he finally said, okay, just get off my back, I'll write it. The idea is if you sit here on Earth and look at a background bright star, like towards the galactic center, and you wait for that star to brighten and then dim, then if you have a nearby star between you, which is moving across the field of view, its mass, by Einstein's theory of general relativity, will bend the light from the background star towards you. And if in addition you have a planet, it will also give a bending of extra light towards you as well. And so that's actually made most clear by this wonderful graphic, which shows you the brightness is measured for Earth here's the background star you're following, and then this foreground star comes in front and bends the light, and then in addition, the planet around it bends a little bit more. So this overall brightening occurs over a period of about a month or so. And that brightening is bright enough that can be done from ground-based telescopes like in Chile and other places. But this little spike due to the planet only occurs over a few hours to a day or so. So you really have to have precise monitoring in order to detect microlensing events. So microlensing events have been done quite successfully from the ground by worldwide teams of astronomers from all different longitudes following an event which is occurring, because you never quite know when that spike to the planet might happen. But of course, it's much better if you can do it in space and just stare at that star. You'll have a much better job of making sure you see everything. So here's a prediction of what might be seen by the Roman Space Telescope microlensing. We're getting back in discovery space now in units on the vertical axis of Earth masses, and horizontally how far you are away from your star. Here are Earth and Venus, and Jupiter and Saturn, and the red dots here are basically what Kepler found. Black dots are the radial velocity detected and a few direct imaging. This is sort of the black dots, which is what was known back in 2006. I showed you on that previous discovery space plot. This is 2019, so by then all these Kepler discoveries are in there as well. So clearly there's this whole class of super Earths or sub-Neptunes that we weren't really expecting to be there, but by golly, they're there, and they're very, very frequently found. The blue dots are just a guess about what might be there. And they're just there to illustrate that the microlensing technique is sensitive to everything above this blue line. So they're expecting to see, their prediction is they might see maybe 1,000 or so planets in here. Certainly if you're seeing a Jupiter or Saturn, you'll be able to detect them very easily. Darker the background colors, the easier it is to see. Earth and Venus and Mars are kind of, sort of right on the edge. You might find a few, but you're not going to be finding a lot of them. And even if you do see a microlensing event due to such an interesting object, there's no follow-up. Once it's over, it's over. You have no idea what the foreground stars. You have no way of trying to find its planets. So it tells you something about how common planets are, their demographics, but doesn't figure any farther along in the way of detecting them and characterize their atmospheres. Okay, what else came along since 2006? Well, we had another bonus spacecraft, the Transiting Exoplanet Survey Satellite. This one was a bit of a bargain. It was a so-called mid-X class mission, $200 million or so. It was launched in 2018. It's been up there and operating quite nicely ever since. It has 4 sort of fly's eye 10.5 centimeter telescopes intended to cover the entire sky, so an all sky survey. The weird thing about it, though, is it's of course looking for transiting. The weird thing about it is it's on this strange orbit in sync with the moon, with a 14-day orbital period, back and forth, back and forth. And that means it's set up to only spend 28 days for each sector of the sky. So if you're looking at one area of stars for only 28 days and you want to see at least 3 transits, that means you're only going to be able to find orbital periods that are transiting of less than 8 or 9 days or something like that. And so if you really want to find habitable worlds, you got to only look around M-dwarf stars, because only M-dwarfs are going to have a habitable zone that's close if the orbital periods of 8, 9, 10 days will get you into the right temperature to have liquid water. So it's basically the whole point of TESS is to not look for sun-like stars, just look at M-dwarfs, which are commonplace. Something like 70% of the stars in the solar neighborhood are M-dwarfs. So there are plenty of them out there, and that's what TESS is doing. Looking at all those, trying to find more Earth-like planets. It's basically found 500 or so candidates so far. Doing well, and it's intended as sort of a finder scope for a James Webb Space Telescope. Basically trying to find planets which are interesting for transit follow-up by a telescope with a really good set of infrared and mid-infrared instruments to do characterization of the possible atmosphere of these planets. So that leads into a James Webb, which did indeed launch successfully in 2021. Should point out that Webb was delayed in launch by roughly almost 10 years and increased in cost by something like a factor of 10. Basically, that's where the money that was going to be spent on SIM and the TPFs went to keep Webb alive. So those of us in the exoplanet community paid a great amount of our lives to help get Webb fly and be a success. So Webb is a wonderful telescope for doing transiting, as well as a lot of other science. It's really designed to do more extragalactic astronomy, of course. That's those who rule the field. But it's not very good for imaging for several reasons. First of all, its secondary is on axis. It has these struts, which means that if you have light coming in from a star that you're trying to occult, these guys are all diffracting light all around, all over the place. In addition, it has this hexagonal tiled mirror. Every one of these edges in the primary diffracts more light. This is probably the worst possible way of designing a telescope to do chronographic studies, and so it's never going to be very good for a chronograph, even though they have a bit of a primitive chronograph on it. But it's great for doing transiting planets. If you just see a planet pass in front of its star, you can measure its light as it both does transits as well as eclipse. Okay, so as it turned out, though, even though TESS was intended as a target finder for James Webb Space Telescope, we got the best possible system for free from a Belgian telescope, the TRAPPIST telescope system, mounted on at La Silla, which is the European Southern Observatory, which you can see from Las Campanas in Chile, just about 50 miles south of our Las Campanas Observatory. The TRAPPIST system is, again, another red dwarf, low mass red dwarf. It's about 1/12 the mass of our sun. So it means its habitable zone is very close in. So look at these orbital periods: 4 days, 6 days, 9 days, 12 days. The weird thing is there are at least 7 planets. They're all lined up that they all transit. Can you imagine all 7 planets lined up in a thin zone with that edge of that orbit pointed towards us, so we can actually see them transit from the ground. And so these are found by because even though they're not really large planets, but because they are bigger than the Earth by a bit, but also the star itself is smaller. So that means you can see a Earth-sized planet around an M-dwarf star, because you're again back to a few parts in 1,000 you can measure from the ground. So we got TRAPPIST for free, and we figured, wow, 4 of these are habitable. This may be our first chance to see evidence for a habitable M-dwarf planet anywhere. Okay, so what happened there? Well, the key things you want to be able to see, we know the planets are there, but do they have in their atmosphere methane, CO2, water vapor, organic compounds? Really want to know for oxygen and ozone. If we saw Amazon packages, that of course would be some sort of life, maybe intelligent, maybe not. I'm not sure if Jeff Bezos read the post that day. But the key thing would be to see if you have methane as well as oxygen, because those two molecules will not live, they will not abide with each other. You have an abiotic source of making them, they will combine, and basically you'll be burning the methane and the oxygen. So if you have both of those molecules observed in the same atmosphere, there's got to be something creating them. And of course, the way that makes oxygen is photosynthesis. The way to make methane is methanogenesis, which means methanogenic bacteria or dairy cows or all sorts of things produce methane. So those are sort of the gold standard for finding a habitable planet that might have some sort of at least small primitive life on it, is look for methane and oxygen or ozone. So that was the hope, to look for that, and especially water too. Of course, we want to see water, because even though we are sort of limited by water-based life here, as far as chemists tell us, they really think water is probably going to be fundamental for life anywhere. So what has been actually found so far? Well, just last year, one of the near-infrared spectrometers on JWST launched that it found an atmosphere around a 3 Earth mass planet. It's 2 Earth radii, so it's probably a little bit puffy. They found evidence in the spectrum for water, sort of a reasonably good. Here's an atmosphere only retrieval. And if you put in the H2O as well, it's not a great fit, but it's by this sort of spectroscopy is difficult, and by the astronomers who spend their life doing this, view that as a solid detection of water. Okay, so we've got an Earth pre-Earth mass planet with water. The problem is it's a hot Earth, 670 Kelvin surface temperature. So this water is probably in the form of steam. So it's not really a place you want to buy real estate. And so that's a good thing. But on the other hand, JWST has spent a lot of time looking at the TRAPPIST planets. Nothing there so far. They are just bare, hot rocks, or I shouldn't say they're habitable zone rocks. They're nice temperature rocks, but there's no evidence for an atmosphere there yet. We'd love to see some evidence for water or something there. It's not been found yet. So that search still goes on by James Webb Space Telescope. Okay, also since 2006, we had yet another decadal survey. It's time for another one every 10 years. And this one finally saw light. In their summary, they said, thou shalt build a telescope wavelength coverage similar to Hubble, aperture of at least 6 meters, with a coronagraphic imaging capability, capable of observing 100 nearby stars and successfully detect potentially habitable planets around at least a quarter of the system. So they're saying, well, we think eta sub Earth, fraction of habitable planets is about a quarter. Should find 25 habitable worlds, go out and build the thing. Take your time. They realize it's probably going to cost at least as much as Webb costs, at least $10 billion or so. And astrophysics doesn't have a lot of money at NASA. But at the time, they thought that something that could fly maybe in 2045. So right now, that has been worked on, being developed. And the key thing it's going to need is, of course, is this coronagraphic imaging here. So to build a chronograph that's as good as required, you better make sure you know what you're doing. And that's one of the nice things about Roman is, in spite of having the microlensing as its planetary component, they also added on a coronagraph as a test bed object, just to see how. Let's build the first purpose-built chronograph, which is designed solely to find extrasolar planets around stars. And here it is, sitting in the test bay out at JPL, just in back April of last year, before we put on a truck and shipped out to NASA Goddard to be mated with the rest of the Roman Space Telescope. I had the honor of being the chair of the independent review team that oversaw the building of this chronograph for the last 5 or 6 years. So it's something I know is going to do a really great job. It's going to prove out the technology necessary to build an even better chronograph that will work on habitable worlds. And here is what the goal is. It's sort of like a discovery space plot, but here showing you the contrast you need to achieve in order to find something. Here's Earth down here at the bottom. I want to get this at 10 to the minus 10 contrast, trying to find Earth next to something which is 10 billion times brighter. And it depends, of course, on how far away you are. The farther away you are, the easier it is to see something. Current ground-based telescopes like the Gemini GPI kind of get you down to the 10 to the minus 6 contrast region. James Webb NIRCam, sort of similar sort of thing. But here's what we're headed for with the Roman chronograph. The originally plan was that the requirement was so-called level 1 requirements, and NASA headquarters to judges to say whether or not the mission was a success or not. They were shooting for something like a contrast better than 10 to the minus 10, but a little bit worse than 10 to the minus 8. They decided a couple of years back, in order to save money, to back off that and say, well, I'll tell you what, if we can get to 10 to the minus 7 contract, this new baseline, we get to this line of contrast, we're going to declare victory and say it's a success. But in the meantime, the chronograph had been designed for, as I said, the last 5 or 6 years to get down here. This is what their prediction is. So they've not really, they will not say it because this is what all they're required to prove. But I believe they are going to get down to this region here. It's certainly down below 10 to the minus 8th, maybe down to 10 to the minus 9th or so. We're still a factor of 10 below or above what Earth will be, but we're going to take a tremendous leap in improved contrast by 3 orders of magnitude compared to what's flying in space right now and what's possible from the ground from with current instrumentation. So we know the chronograph works. In the test bed, we're going to find out when Roman flies in 2027 how well it works in space, and then we'll be ready for the Habitable Worlds Observatory. So that Habitable Worlds is being developed right now by teams at Goddard. They're opening it up for other astronomers who are professional astronomers want to get involved with and serve on the teams. This is an image of what they sort of think it will be able to see. If you can block out a sun-like star at the center, you might be able to see the Earth off here to the side. sort of this is assuming it's our solar system. So it's sort of Earth here and a Venus there and a Jupiter here and a Saturn out here. This is sort of literally the scale that they think you might be able to see and resolve with that telescope. They're not quite sure how to build the thing right now, needless to say. But given it's being built at Goddard, where they built Webb, there's a certain preference there for segmented primary mirrors, in part because it can be folded up and fitted into a smaller launch fairing. Although maybe that 9-meter fairing of Starship may change that at some time, but we shall see. But that's one of the technology developments underway right now, is to figure out how to build this thing and have it work, and especially how to make a chronograph work with this segmented architecture. I'm actually chairing concurrently the Exoplanet Exploration Program Technology Assessment Committee, and we're right now trying to understand the efforts that are being done by several groups to see what would happen if you have a segmented primary. It does make it harder. So it's planned for 2045, 20 years from now. Hopefully it will work and we'll have all the bugs figured out of it by then. Okay, what else came out of Astro 2020? There's also the idea of what can be done from the ground. And in the US, there are two competing programs. There's the Caltech-led 30-meter telescope, literally 30-meter in diameter telescope. And there's the Carnegie-led Giant Magellan Telescope, which would be a 25.4-meter telescope. The problem is they both put a lot of money into this. They brought in many partners, university partners, international partners, but they're both short of money. And they figure they need about $1.6 billion, and they're trying to pitch this to the NSF, as not only get NSF to help build it, but also help to run the thing. So this sounded like a pretty good idea back when this was proposed back in 2020. But of course, in our current administration, NSF, I think I've read that there's a proposal to cut NSF's budget in roughly half, in which case you can be sure that if anything like that happens, this will never be built with NSF money, that's for sure. But let's assume that somehow NSF is able to support this, or else these two projects can find money somewhere else. There's a lot of exciting science that can be done. Here's an artist's image of what the Giant Magellan Telescope might look like when it was built. This grandiose housing. It's no longer a classic dome. It's a sort of a boxy shape for letting wind blow through, with open panels to let the wind blow through at night. And you really want to not have anything called dome seeing. You want to have your temperature inside the dome, and particularly if your optics at the same temperature as the night sky, because otherwise, if it's warmer, it's going to be convecting heat all night long and making your images blurry. So you want to come to equilibrium with the night sky temperature quickly. A nice big boxy dome like that does it. And one of the motivation, in fact, the primary motivation for the Giant Magellan Telescope is if you go to their webpage and look to see what they're doing, their first graphic says, find Earth-like planets and search for signs of life. Okay, well, I've got to cheer that, clearly. That seems to me like a pretty sound motivational thing. And the nice thing about the GMT is it is well suited to find evidence for an atmosphere around the closest Earth-like planet we know of, which is Proxima b. Okay, we told you about Barnard's star. That's the second closest stellar system. The closest stellar system is Alpha Cen, which is a binary system. You can't see it here, but there are two solar type stars about 17 AU apart. And here's Proxima inside this red dot, this red circle. There's a really faint red dot there. That is Proxima. It's a red dwarf, about 1/8 the mass of the sun. And one of our postdocs from Carnegie, Guillaume Gladys-Godet, led a big effort of radial velocity machines in the southern hemisphere pounding away on Proxima every night they could for years, and they found evidence for this planet here, 1.3 Earth masses, an 11-day orbital period, which is the habitable zone of this red dwarf. So we know it's there. What we don't know is if it has an atmosphere, and it's not a transiting. If it was transiting, we might know by now if it has an atmosphere. This is one we have to actually image it with a telescope like the Giant Magellan Telescope and see what it can do. And GMT, this again shows you a sort of a contrast discovery space. We think Proxima is somewhere here. It's only about 10 million times fainter than its red dwarf primary. And depending on where it is in its orbit, it'll be somewhere on these distances from the star. The GMT is thought to be able to measure planets anywhere in this box. And so it can actually find Proxen in some parts of its orbit. WFIRST should have the precision, the contrast to see it, but WFIRST is only a 2.4 meter telescope. It's just like Hubble. GMT is 10 times bigger, so it can actually probe in closer to actually detect Proxen b. And of course, what we're really headed for is down here. This is where the Habitable Worlds Observatory will do its great job. Okay, so here's how will GMT be able to do this? It's going to have an adaptive optic system, which is what you need to remove the effects of the Earth's atmosphere. It'll be a very delicate thing to do, but one of the key targets they're looking for, they hope to maybe study, these are all, by the way, known planets that have been found by other techniques, primarily radial velocity, but some transiting. And they will be able to find Proxen b. There it is. This is big reddish dot here, M 5.5 star, that is Proxen. So that is the one that for sure, if we get GMT built, we'll be trying to look for it. Of course, there's a bit of a race there because the Europeans are building their own extremely large telescope down in Chile. They will have access to Proxen also. I should point out, by the way, that the TMT will not be able to see it because this is a southern hemisphere star. You cannot see it from either of the TMT sites, either Hawaii or in the Canary Islands. So GMT will be competing with the European extra large telescope, extremely large telescope to find, see if they can be the first one to find an atmosphere on Proxen b and perhaps find our first habitable world. One other thing that GMT will have is a really high precision radial velocity spectrometer. Most spectrometers these days have roughly 1 meter per second precision, sort of one of these curves here. And that's sort of the state of the art. But a lot of people are trying to figure out how to get to extreme precision radial velocity down to, say, 10 centimeters per second, because that's what you need in order to find Earth. Earth is about 9 centimeters per second. And so GCLEF will also be an important instrument on the GMT. Okay, so that's where we are. Here's what the mountain looks like in Chile. We don't quite have the structure built, but the mountaintop has been leveled. I remember being there and watching at noon, looking towards the top of Los Magellan Peak and watching the explosives blow dust clouds in the air as they were leveling the mountaintop. So the infrastructure is there, the background, these towers and buildings, support buildings are there, but we just don't quite have the telescope and its gorgeous housing yet. But at this point, they need 7 mirrors altogether. 3 of them have been completely finished, 4 of them are in progress. So they're moving ahead with this, even though they're kind of going to run out of money at some point. Now, where are we finally for conclusions? Here is back to the Discovery Space plot I showed you early on, all sorts of radial velocity planets, transiting planets, and nothing much here around Earth and Venus. That hasn't changed. Some more Jupiters are here. There are some Earth's mass planets, but they're typically around M dwarfs. So we still don't quite have the ability to find Earths and Venuses around G-type stars out at 1 AU distances. It will take Habitable Worlds Observatory to do that, I'm afraid. But there is some good news. We do have Proxen b right here, this yellow dot. It's we know it's there. And I've said GMT knows how to take its picture and see if there's something in its atmosphere. There's actually possibly a Proxen c, which some people dispute, and a Proxen d, which is perhaps more likely to be real, but Proxen b is definitely real. And what's really interesting in this plot, why I show it, is that there's also, you notice, Barnard b. This is a sub-Earth mass planet around Barnard star. Wouldn't it be great if Peter Van de Kamp was still alive and he could realize, hey, you know what? Maybe your Jupiter mass object around Barnard star wasn't real, but by golly, Barnard star has a sub-Earth mass object. I think that would really make Peter Van de Kamp sit up and clap. So thank you very much. That's where I'm going to end things tonight. If you want to know more about the history behind all of this, I've written a number of books on this, which are presumably available on good old Amazon, courtesy of Jeff Bezos or other places. And I'll be happy to take some questions, either verbally or on the chat window, or however we want to handle this.
I got a question. Thank you, Alan, for the interesting session. I got a question though on the hot Jupiter.
Yeah.
How does that work when you have a gas giant next to a star? Doesn't the atmosphere or at least the gas starts blowing away, or does it become more hotter and more active?
But that you're exactly right. That was one of the things that I and the other referees for the Nature paper were worrying about, was that it might basically be photoevaporated by the high temperatures. But if you actually do the calculation, it turns out it will take a hot Jupiter something like the age of the universe to completely be photoevaporated down to much lower masses. On the other hand, there are other planets where they so-called hot Neptunes, where we think their atmosphere is being photoevaporated, and there are actual measurements. I think it's HT 294558b, which is another one of the hot Jupiters. It was actually observed by Hubble early on to have atmospheric mass loss. They could see in the spectra what was going on, that the mass is being lost. Light was being given off by molecules or atoms actually being photoevaporated from the surface. So if you're a hot Jupiter, yeah, you're in some danger. And there's actually some evidence that some poor gas giants might actually get photoevaporated down to become Neptunes or something like that. But it's kind of a hard thing to do. So they're sort of living right on the edge. But you're exactly right. There's a danger of losing it, and being stripped down to a rocky core. And that's something people argue about, is when we do see some rocky cores in close, they wonder, do they form as rocky cores, or are they the stripped cores of hot Jupiters?
Thank you very much.
You're welcome.
Any other questions?
By the way, I should say I was impressed by all the commentary that you gave while I was listening to your meeting ahead of time. It's really, I'm impressed with how much work you guys are doing and how many people you have involved. That's wonderful stuff you're doing with your club.
Well, we certainly appreciate. Looks like we have another hand up. So it's like George.
And what about when Fox Santa's a red star and produces lots of flares, right?
Yes.
Is anyone monitoring its flaring progress these days?
It's monitored continually because of want to make sure if those other possible planets are there or not. But you point out one of the downsides of habitable worlds around M dwarfs, which I did not touch on. Around G stars like the sun we have flares, but they're not normally that bad. But M dwarfs are fully convective, which means they are flaring and they are very active in terms of giving off deadly particles and radiation. So that's a drawback. You might have a planet around an M dwarf that has a watery ocean, but if it's getting blasted by flares and highly energetic particles from the M dwarf, you may not want to live there. So good and bad M dwarfs. So you're exactly right, though. We need to know more about the flare activities on those stars to really be a place where you want to set up a real estate office.
So any other questions tonight? But anyway, sir, thank you very much for your time. Novak very much appreciates you taking the time. We have over 50 events this year with our 1,200 members, and we're one of the largest clubs in the United States. So we certainly hope you'll come out to something. We have some in almost every. I didn't really mention it because we were trying to catch up. We had over 1,000 people at Uvar Hazy last night, and we have lots of people at Five Meadows all the time. So we certainly would love to have you visit with us in person. But we do this every month, and we have lots of things going on our website. So again, thank you very much on behalf of the club. And do I see other? No, these are just the clappings, and certainly it was a great presentation, and we appreciate you.
Thank you. Have a good evening.